Hi guys, let's talk about buoyancy, how things float, and how even if things are sinking, they still have buoyancy force. In class we derived buoyancy, so I'm going to shortcut and skip the definition and go straight to the equation. If you recall, the buoyancy force is if we have a block or any shaped object submerged in a fluid, it's the net sum of all of the pressure forces. So not gravity, but just the pressure forces. We sum, and that total is the buoyancy force up, because these are larger on the bottom because they are at a greater depth than the forces on the top. And it ends up being the volume of the object which affects its buoyancy. We should be careful to distinguish from submerged volume and total volume, because if we were to do the same derivation for a partially submerged floating object, the top of the fluid where the pressure stops, so to speak, those force vectors cease to exist, is at the top of the fluid, not the top of the object. So it's the submerged volume or the displaced volume that creates the buoyancy. So there's a few things I want to mention in this video. The first is Archimedes Principle, and the second is some examples, though the examples I think will be in a separate video. So let's just do Archimedes Principle and talking about partially submerged objects. So here we go. What Archimedes' principle says, if you notice how in general weight is mass times gravity, of course, that's obvious, don't forget that. But if we, instead of mass, write density times volume, then weight is density times volume times gravity. In general, just in general, we have density times volume times gravity is weight. But look how here we have density times volume times gravity, which means that buoyancy force is the weight of something. So look at this for a second. It's the density of the fluid as opposed to the density of the object times the volume of the object. So even if it's not completely submerged, it's the amount of fluid that is displaced. So sit with that for a second. It's the amount of fluid that is displaced, even if it's partially displaced or completely displaced. This is the amount of fluid that's displaced. This is the density of that fluid. Density times volume gives mass of that displaced fluid, times g gives weight of that displaced fluid. So we can summarize our analysis here with sinking versus floating. And this is important terminology that I'm saying with my words, that I'm not going to write with my little pen, so make sure you write this down somewhere. In order to sink, an object's buoyancy must be less than its weight, But said in terms of Archimedes' principle, how would we word that? Well, sinking means that the density of the object is greater than the density of the fluid for sure, but in terms of Archimedes' principle, it says that the weight of the object, so notice I'm writing this in math, but I'm saying it in Archimedes' principle words, the weight of the object is greater than the fluid it displaces. So the weight of an object is greater than the fluid it displaces. If it has a more density, then the volumes will be the same. So the weight of the weight of the object will be greater than the weight of the fluid it displaces. Cool. And of course, floating, it's the opposite. Everything's the same, but we have everything flipped, meaning the density of the object is less than the density of the fluid, so it goes up, which means that the object weighs less than the fluid it displaces. So if the object weighs less than the fluid it displaces, then it flips. Cool? I hope that makes sense. So let's switch to and of course you can pause and rewind if you need to bring that screen back. If something is partially submerged, say we have some density, say I have an object of specific gravity equal to 0.8. What percent is submerged? Well, the first thing we do, and anytime you ever have something floating on the surface, this is what you do every time. You draw your two vectors. Boom, buoyancy up. Because there's some fluid being displaced, right, versus V total, which is the total volume of the object. V sub is the submerged volume. Since we have some fluid being displaced, therefore we're going to have buoyancy. And of course, down is mg. So sorry, these arrows aren't part of the force diagram. These arrows are your force diagram. Think about it for a second. If it's floating there, which is bigger? Well, I hope it makes sense that if floating, meaning sitting still on the surface, it's just bobbing there, the net force of everything is 0. Therefore, the forces cancel. You get up equals down in terms of magnitude, right? I know one is negative and one's positive, but in terms of magnitude, boom, they have to equal each other. They have to cancel. Up equals down. This is how you do equilibrium. So it's an equilibrium scenario. In our other scenarios, if it's sinking, it stays sinking. It will always accelerate downwards. If it's floating, it will always accelerate upwards. So rho fluid V submerged G equals density object V total G. So be careful now, the mass of the object depends on its total volume, but the buoyancy force only depends on the submerged volume. So here we can only cancel G, and we end up getting that for something floating on a surface, we get that the ratio, so if here's what I'm going to do, a little fancy algebra. I'm going to divide both sides by V total, and I'm going to divide both sides by density of the fluid. So I end up getting a cool little ratio here, which says that the ratio of the submerged volume to the total volume is the ratio of the object density to the fluid density. Isn't that cool? So it's just a ratio. So here's how I always remember this. The smaller number is on top. So what does that mean? Well, clearly the submerged volume is less than the total volume, and if it's floating, well, hope this makes sense now that its density is less than the fluid density. So this is a smaller number because it's less dense, it's floating, and this is a smaller number because it's only partially submerged. So look, if the specific gravity is 0.8, that means actual density being 800 kilograms per cubic meter. The point is it's 80% is dense, which means V sub ratio to V total will be the ratio of the densities, if we assume this is water. Okay, of course we're assuming H2O here. Then it'll be a ratio of 0.8 submerged, or 80% submerged. Isn't that cool? So if it's 80% is dense, it's 80% is submerged. So notice how, here's a fun little example, if you yourself, as a human, float in water, humans tend to float, but notice how if you sit in water, only the littlest part of you is above the surface, right? Why is that? Well, your specific gravity is like 0.95 or 95% or 98% depending on who you are. So only 2% or 5% of you is above the surface. And of course you want that part to be your face, unless you're holding your breath. And of course it's easier to float if you take in a breath. So if you're floating in the ocean, of course it's easier to float in the ocean because the density of the ocean is larger. It's easier to float in the Dead Sea. It's why they call it the Dead Sea, because this number is larger. But in order to float in any water, it's best to take in a breath, because that lowers your density, lowers this density, so therefore lowers the amount submerged of your body. So more of you can stay above. Yeah, it's a cool example. The ratio ends up making sense. Tune into the next video for a simple example of force diagramming when it's not in equilibrium, and I will see you then.